Okay, so if I increase the number of line pairs significantly in a small distance, the wave will have a higher frequency. I refer to the first signal as low frequency and the second signal as high frequency. Okay. The help shown in the picture, any help present in any picture in the world, appears as a factor. How? It appears like dots like this, meaning we always hear that there is a white dot. We hear this topic often. 1 second. Hello, doctor. Do you know that I am doing something for you here? Sorry. I am here in the area doing something for you here. We are heading home from the American city. I think he told us about the home.
The American person in the last week did not come home from there. Yes, he did not confirm the arrival home to the American city. Yes, I told you whether you know or not. Yes, okay, thank you very much.
I'm sorry, but this is too much. Noise, as we said, always appears like this. You feel like there's noise in the image. You always sense that the image isn't sharp or has white spots and the image isn't complete, right? We always recognize a noisy image by the presence of incomplete information. For example, each pixel has information, and if one pixel has information while the adjacent pixel has missing information, or if the two don't have the same value, then the image isn't homogeneous, right? Now, let's assume I have a group of pixels with very high noise. This means that each pixel contains a different value from its neighbors, right? There is a significant change. Well, if we assume that there is information and there is a gap and there is information, there is a significant change. This change represents a large change in the signal, a very large change. High frequency indicates noise, representing things that have sharp features, such as edges. For example, bone compared to soft bone and air shows high contrast between them, or signals that come to you with more resolution or more contrast for two organs. However, there are also variations in people's devices. Here, high frequency refers to the signal coming from an object that has high contrast with itself. On the other hand, low frequency represents the signal coming from an object that is homogeneous with itself. So when I say I want to apply a filter, what does filter mean? It means I want to remove noise from the incoming signal. Should I remove noise in high frequencies or in low frequencies if I want to eliminate noise? In the way I picture it and according to what I want to see, if I want to remove it. So I have now applied a filter that allows low frequencies to pass and blocks high frequencies. The high frequencies represent elements with very high variation, such as bone and soft tissue, for example, bone and air. If there is noise present, there is variation between the pixel with noise and the adjacent pixel. So when I say I want the high frequencies to pass, you will find the image becomes more sharp and more noisy. This is because I allowed the high frequencies to pass, meaning my filter lets through only the high frequencies that remain in the image. Now, if the frequencies represent the signal with low variation between them, I did not allow those to pass, resulting in a high-pass filter. The high-pass filter will allow high frequencies to pass. increasing the noise present in the image, while the low-pass filter will allow low frequencies to pass, making the image smoother. The bandpass filter will select a range of frequencies, which is what I want. The filters we see in devices tell you to increase sharpness and increase smoothing based on this idea. Depending on whether you choose a high-pass filter or a low-pass filter, smoothing is something you work with in the low-pass filter, but at certain degrees. As for the high-pass filter, you are working with noise. The sharpness you are increasing is enhancing your resolution, meaning you are working with the high-pass filter. The band-pass filter is something in between the two, applicable to all machines and imaging modalities. The company has something in the background that I don't know about, which ultimately gives you a commercial name to work with, like Smooth 1, Smooth A, Smooth B, Smooth C, Sharp A, Sharp B, Sharp C. The sharpness has something specific in the background. For example, if you want to perform smoothing, it tells you about smoothing methods. It does something called averaging. What is averaging? This image and these pixels want to remove the light. So you will do something called averaging. What does that mean? It means taking a group of pixels like these, for instance. You check the values of these pixels. How much is this one? How much is that one? And so on, repeatedly checking the values of the pixels. Here is a value of 15, a value of 13, a value of 3, a value of 4, a value of 6, and a value of 1. Okay? I want to take all of them, sum them up, and divide by their count. So you are essentially doing what? You are doing averaging, you are doing smoothing. Then place the new value at this point and take the next pixel. Look at the 5 or 6 pixels around it. Perform a new averaging and move to the next pixel. Take the surrounding pixels and perform a new averaging. In the end, what will you get? You will get an image that is homogeneous, where each pixel is close to the values of its neighbors. So, you have done smoothing. This is one of the methods of filtering or one of the methods of smoothing that occurs. All right. I have We remember together the topic of grayscale, window level, and window width. And we used to say that all my values are placed on the grayscale. Then I start to change the window width and window level to enhance the image. If today I need high contrast in the image, I should keep my window width, either low or high. I need more brightness in the image, so the window level will adjust the brightness and the window width will adjust the contrast. All right, we were talking about this. The window width here, for example, is large in this image, so the contrast is affected. The window level here is high, which will increase the brightness of the image significantly. All right? If you want to reduce the window width, your contrast in the images will increase. Your contrast in the images will increase if you reduce the window width. This is what we do with our images. We move the mouse and change it. This information is different in window width. 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 This information is specifically available in digital imaging work because the digital subject has a wide range of exposure. Therefore, I can control my window level and window width and manage the existing brightness. For example, this image has a high window level while the window width is large, so the image lacks contrast. Now you will find the image, for example, this is the same window width that exists here in ST but it started to reduce its window level. The window level of this image is the same as the one in ST. It is the same window level value, but it played with the window width, creating an intermediate state between the first and second images. Controlling windowing affects two things: brightness and contrast. The window level adjusts the entire range on the grayscale, whether you are moving towards brightness or darkness. Contrast is adjusted by window width. If you increase the window width, you decrease the contrast in the image. Conversely, if you decrease the window width, you increase the contrast in the image. This is important depending on what you want to see, like in the brain where we reduce the window width to provide more resolution or more details between white matter and gray matter. You want to differentiate between objects that have low differences in their attenuation, unlike the bone window or the lung window, where your window width is large, 3000 or more, depending on your machine. This is because you are trying to highlight the bone in relation to the other tissues, so the contrast doesn't matter much since the bone will be clearly visible in the image. There is also something called temporal frame averaging, sometimes if you are working on ST. If you are working with a slice or image with a thickness of 1 millimeter, will the image be noisy or smooth? It will be noisy, right? So you have to increase the thickness. The thicker the slice, the smoother the image will be, correct? What happens is that you are stacking a series of images together. Stacking is the averaging. That occurs here between the frames displayed in fluoroscopy, which reduces the noise present. For example, this is frame 1, this is frame 2. If you average or stack them together, the noise decreases. The more you increase the number of frames you stack and average together, the better it works. This works very well with static images, not with dynamic ones. So, what is the difference between static and dynamic images? Static means you have two screens, one displaying video images. When you are working dynamically, you see an image every second or every 1 second, and there is another screen displaying what I call fluoroscopy and fluorography. Fluoroscopy is the image that moves with you dynamically while you are working. You are seeing an image that keeps changing. Frames. On the other hand, fluorography is when you take a still image, like a spot, and sometimes you have to increase the milliampere values because if you are taking fluorography, you need to reach, for example, 100 milliamperes. Unlike when you are working on the fluoroscope, where you might set it to 5 to reduce the overload on your tube. So you are continuously taking many frames to allow you to work on your procedure for an hour or two, or however long you are working in a static manner. Okay? You might find that there is something called lag, which is the delay. What is lag? Do you remember the topic of the camera, or essentially the camera that takes the image from the story? Back in the day, they used a camera. What happens in this process? What is my image? This image comes from my phosphor output and goes to the camera or the electronic camera. So what form does it take? In the form of light photons. If these light photons hit the surface of this camera tube, the photocathode will convert this into electrons. Each collision point between the incoming electron from the image will have an electron here. Well, there is a collection of electrons on this surface and this electron. Well, the number of electrons will be compared. You were not bored. For the intensity of light that falls here, the intensity of light comes from a large point or a large intensity of light. So the number of electrons that will be in this particular spot will be high. The next point will have fewer electrons, so the number of electrons at the next point will be less. Depending on my image and the electrons that are coming to me, I will have electrons present on my photocathode or on the screen. The camera tube has electrons that act like a cannon, shooting a continuous stream of electrons. This stream of electrons moves across the screen, scanning it back and forth. As it moves, if it encounters a point with many electrons, what will happen? It starts to move and pass through, and as the electrons collide with each other, they begin to move together. It starts with the translation of the signal, which results from and involves collisions between electrons and existing electrons. Each signal comes with a certain strength and magnitude of intensity according to its current flow. This current depends on how many electrons were originally present due to collisions caused by incident lights, such as those coming from sources like lamps hitting photocathodes. Then signals reach images shown here in picture 2, according. These signals start giving off more electron emissions colliding again against said cathode surfaces, thus generating visible lighting effects, translated into my image while simultaneously scanning via camera tubes positioned precisely there. The pilot is moving the signal, and at the same time, this translates that point into an image and displays it on your screen. What does it display on your screen? There is synchronization between the point you are hitting with the initial gun in the camera tube and the point you are translating to the output or your picture or your image. This synchronization is very important. Very important. Okay? If the response time changes, for example, if a signal comes faster than another signal and I receive an image every second, when the first image is disappearing and a new signal arrives, what happens? There is a delay. And this delay can cause problems or affect the appearance of the output image. The output image is a result of the response delay due to a lack of synchronization or incorrect timing of your signal. These were all issues that existed, but when the CCD technology was implemented, it resolved these problems. However, this information is important for you to know. Are you sure? What happens is the delay that occurs. This is the delay that happens, or the delay that occurs. This is what causes the problem of the image appearing this way, or the image appearing like this. This is the delay that was before, and this is the new one. So you see this lag or delay happening. This delay was obviously present in older image intensifiers, which could have a lag time of about 30 to 40 milliseconds. However, the current image intensifiers have a much shorter lag time, now down to 1 millisecond. This lag can also occur if there is an issue with the television itself or the video system. So, I have two sources of lag, one that may depend on the signal coming from the image intensifier, and the second type I mentioned could be caused by the video system
or the circuitry in the television. As I explained earlier, if there is a problem with the incoming signal, this issue can be resolved. Now, I want to explain something important here. There are some filters that have a feature called edge enhancement. What is edge enhancement? It is a process where you have an image like this, and the field of image processing is very important and has helped us a lot in solving many problems in images and enhancing image quality. You have an image with a certain number of pixels, and this other image has the same number of pixels. You can perform what is called subtracting one image from another, or combining two images together, performing any operation between these two images. This is done through the pixels themselves, meaning you know the value of each pixel and what it represents. It subtracts the values from each other, taking the values from the pixels of the first image and the next image, and produces a result. They use this concept to enhance image quality in one way or another, like using the edge enhancement filter. If you want to produce an image like the one we see here, with sharper edges, what do? I have an image like this. So if I apply a little bit more smoothing to this image, what will happen? It will appear that I will look like this in the image. How does smoothing work? It means essentially a filter that performs smoothing or the averaging topic that I talked about. After I applied this smoothing, the values of all the pixels in the image became very close to each other, resulting in a smooth image. If I subtract the smooth image from the original image, what will I have? You will have essentially the part that has high density or high signal. It means that the elements that are smoothed out with the individual pixels in the photographic image are now only the high density signal or the high signal or the high intensity signal that is present in the edges of my image. So, you have an image that contains high intensity signals coming only from the margins or edges of your original image. Then, you add this edge image to the original image to enhance those edges or improve your contrast. So, this is the edge filter. Therefore, all these filters are operations that take place in image processing, aimed at what you want. You want to reduce noise, enhance a certain contrast, or apply blurring, for example, and increase smoothing. The whole idea is that I work on my pixels and improve their values, see which pixels are around them, and start averaging them out, such as if I subtract the values I applied from the original image, what will I get? I will get the areas with high differences, which are the high densities or high intensities. I take that and add it to the original image, so I have maximized the difference of the objects from the background, resulting in the image appearing this way. Now, digital subtraction angiography is one of the techniques available and is used in interventional radiology. For example, in cases like cerebral angiography, carotid angiography, or orthography, consider any case where a dye is used and you want to see the arteries clearly and enhanced. Of course, if you take a picture, you will find the dye inside the bone, meaning you cannot see well. So, a technique called digital subtraction angiography was developed. What is this technique? What is its function? And how does it work?
It tells you that before I take, for example, an image of the carotid area, I will take a picture before injecting the contrast agent. This image will give me all the small muscles, but since the contrast agent is not present in the small muscles, the contrast agent is not illuminated. The image that I obtained is called the mask image. This image contains data and information about all the small muscles. After injecting the contrast agent, I will take another picture that has the same information, but includes the arteries with the contrast agent. I will start to perform subtraction between the two images by subtracting the mask image from the post-injection image, which will reveal the vessels alone because I removed the muscle part and the soft tissue part, so the vessels appear alone in the image. This is digital subtraction angiography. Sometimes the patient may move while you are taking the contrast agent image, and the first mask image must have the patient in the same position and the same condition because it subtracts pixel from pixel. If there is a shift in the pixels, it will take a different value.